Hi, my name is Chris Clark. I'm Production Engineering Manager for Liberty Resources. I'll be talking about our third segment of integrating hydraulic jet pumps into our full field development north of Tioga, North Dakota. First off, I'd like to point out that on this graphic that we've got a total of 8 1,280 acre DSUs where we're installing, or have installed rather, an infrastructure corridor to gather up all of our fluids, that being oil, gas, and produced water, and then also to deliver fresh water for frac operations as well as day-to-day production operations. The reason why we're doing this is to remove trucks off the road, trying to be good neighbors. The main objection for most people in and around oil and gas operations are trucks on the road, and we feel it's being a good neighbor to get these off the road, as well as it does make economic sense to do so. Tying in this infrastructure corridor into our full development plan, where we're putting up to 3 tank batteries, or pardon me, 3 drilling pads per DSU. In a 1280 DSU, we're putting in up to 10 wells per DSU, and on a 2560, we're putting up to 20 wells per DSU. On each of the drill pads, we're drilling up to 8 wells, depending upon the existing spacing that was already there, and then we're flowing all these wells back into a central facility, as shown on this graphic. From the central facility, we're then tying into our infrastructure corridor, where we're taking our oil to sales, our gas to sales, and we're taking our salt water to a disposal well, and then we're also bringing in fresh water for our operations. Key to this central facility is our central process flow, which does integrate into our hydraulic jet pumps. Relative to normal tank batteries, where we've only got up to 2 stages of separation going through a 2-stage separator and a 3-phase treater, we actually have 4 stages of separation in our process. One, we have a dedicated treater for each and every well, where we're measuring oil, gas, and water so that we have good reservoir management, and we can see what well performance is at any given time, and not necessarily waiting between well tests to determine where we have production downfalls or for that matter, production upticks. The second stage of our separation is actually our power fluid vessel that is an integral part of our artificial lift strategy, where we're pulling off power fluid into our hydraulic pumps to lift our wells. The third stage of the separation is a 3-phase vertical treater. We then flow into a vapor recovery tower, and then finally into our tanks. One of the reasons why we're doing this is we're actually yielding up to 5% more oil with multiple stages of separation than you can out of just 2 stages of separation. We've demonstrated this through PBT specific to our oil in this particular field. So this next set of slides is really showing some pictures of our tank battery layout. Now, we spent the time working with an engineering firm to put together 3D renderings of our facilities. This enabled us to really optimize how our pipe was laid out, as well as to mitigate building mistakes that can occur if we're just going off of 2D drawings. One of the reasons why we are going with central tank batteries is to minimize the amount of manpower that it takes for us to operate the wells that we're going to be putting in this play north of Tioga, North Dakota. By putting in the central tank batteries, we've centralized all of our moving parts using a utility corridor to minimize trucking. And then we have also a single point of chemical treatment. So managing our chemical inventories in the field is significantly easier than if we're spreading them out over multiple tank batteries. We're also going to be managing a lot less equipment with fewer treaters, fewer tanks. There's less chance of spill, that type of stuff. So we see this as a less risky method to produce our wells from an environmental perspective. The other thing that really comes out of this is we're really able to maximize the utilization of our automation. We plan to, and are in fact integrating all of our automation into our production software to be able to operate our wells by exception rather than visiting wells each day and trying to do things on a scheduled basis. We're again doing it by an exception basis, doing it real time with the data that's coming in. The other thing that comes about using central tank batteries is we can significantly reduce our emissions and significantly reduce the amount of maintenance that's necessary by centralizing all of our facilities, and specifically the artificial lift, our hydraulic jet pumps, and the prime movers that are getting our jet pumps to lift our wells. An advantage to also centralizing all this equipment is that as regulations change, we have fewer places to install anything that's necessary with increased regulations, whether it's air emissions or spill containment, whatever those changes may be, we have fewer places to install those. And then another major piece to this that Liberty feels is very important is our production volumes at the wellhead. That enables us to have good reservoir maintenance and good reservoir surveillance. And again, we're able to react to the wells on a day-to-day basis because we see what the production is rather than rotating through possibly a weekly well test or something that may be more or less frequent than that. Where this central tank battery concept ties into our artificial lift, again, is we're able to, with jet pumps, install relatively large hydraulic horsepower in one centralized location, lifting multiple wells with one pump, or lots of wells with mini pumps. But again, minimizing the amount of moving equipment. We can also, using the power fluid vessel that we have, we can run on either power oil or power water. We do see it being advantageous to run on power oil. The produced water in the Bakken is very salty, has up to 250,000 parts per million chlorides, and we use power oil because it has a lot more lubricity, and we see that we don't have to do near as much pump maintenance, as well as utilization of chemical does go down when we're using power oil. The jet pumps will work up to a certain point in time in the well's life from an economic perspective. When that cutoff comes, one of the things that we will be able to do with this centralized design is actually go to a hydraulic piston pump. We do have the flexibility with this type of a central tank battery design to move from one artificial lift method, being jet pump, to another being piston pump, without any incremental capital. The other reason why central tank batteries make an awful lot of sense is when you look at your lease operating expense, and to give an example, here is a graphic of Liberty's lease operating expenses from our most expensive category to our least expensive category. Most expensive being produced water, trucking and disposing of it, our labor, our fuel, power and electricity, our heating, and then other subsurface equipment. With the central tank battery design and the infrastructure corridor, we're really hitting on those top two categories where we're spending upwards of 80% of our lease operating expense. Using our infrastructure corridor, we're gathering our produced water, taking that to a company-owned saltwater disposal well, and taking third parties out of the equation there. The second part is we're attacking our labor by centralizing all of our moving parts into one place and minimizing the workforce that's necessary to do this. This also piggybacks on the idea of operating by exception, using our data that we're gathering through our automation. From a capital perspective, why does it make sense to do this? You may look at all the equipment we have out there and think this may be significantly more expensive to install. In fact, it's not. They're about equivalent. In Liberty One, when we were building our single well tank batteries, we were roughly $1.3 million per well to install the tank battery, the artificial lift, as well as the tubulars and our spill containment. In Liberty 2, we're roughly about $1.2 million. So on a cost basis, we're pretty comparable Liberty 1 to Liberty 2. But we're getting a lot more out of our dollar in this instance with Liberty 2. As I had mentioned earlier, we're getting 5% more yield out of our oil because of the numbers of stages of separation. We have cement-treated pads in this cost of $1.2 million. So our pad maintenance, which can be upwards of $200,000 a year depending upon the year, is mitigated. We have improved containment systems for spills. We're using fully lined containment, whereas in Liberty One we were doing dirt and clay berms for our spill containment. We've also incorporated a vapor recovery unit where we're able to reduce our emissions and meet the most stringent standards that are in the U.S. today. And then again, as I'd mentioned, we're getting increased revenue through our increased oil. We do expect those costs of $1.2 million to come down. That was on our first build. So as we progress down the road, we will see some efficiencies on that, and we do expect to get better performance with that. So in summary, with Liberty's newest development north of Tioga, North Dakota, we've got a consolidated land position where we've put in an infrastructure corridor to gather up all of our produced fluids as well as distribute fresh water for all of our operations. We're utilizing central tank batteries and an integrated artificial lift approach with hydraulic jet pumps to lift multiple wells from one location. We're using this to operate by exception, minimize our manpower, and ultimately we should be seeing a lot less, or lower rather, capital expenditures to develop this property.